Hello students, so today our lesson is the halogenation of alkanes. Now alkanes, as you learned before, they are saturated hydrocarbons, and as such they do not carry out a lot of reactions. They do mainly combustion, halogenation, and cracking. Now we're going to focus mainly on halogenation because you've learned about combustion and cracking already, right? Now, suppose you want to chlorinate methane, meaning you want to add chlorine to it. Well, we carry this out by means of a substitution reaction, right? So, here's our methane molecule, and we add chlorine to it, and we need our UV light there as a photocatalyst. Then we'll have one of those chlorine atoms in the molecule substituting one of the hydrogen atoms, and so we get CH3Cl, and the hydrogen that came out bonds with the other chlorine atom to form HCl, hydrogen chloride, not hydrochloric acid, hydrogen chloride. And this of course is called monochloromethane. Monochloromethane because this can be a chain reaction as long as we have enough chlorine and the UV light is still there. A chain reaction in which all four hydrogen atoms eventually get substituted. So it doesn't have to stop at monochloromethane. Our reaction can continue. The monochloromethane that forms reacts with more chlorine in the presence of UV. This time again, one of those chlorine atoms take the place of another hydrogen, and we get CH2Cl2 plus HCl, and the name of this one is called dichloromethane. Then, like I said, the chain reaction continues. Dichloromethane plus chlorine, one of those chlorine atoms take the place of another hydrogen in here, and that hydrogen comes out and bonds with the other chlorine to give us HCl, and then we have CHCl3, right? So one of those hydrogens removed and replaced by a chlorine, and this one is called trichloromethane. And finally, we take our trichloromethane, react it with some more chlorine in the presence of UV light, and one of those chlorine atoms take the place of the last hydrogen that's there, and we get CCl4 plus HCl. All four hydrogens have been replaced by chlorine, and this one now is tetrachloromethane. Alright, and then the reaction will come to an end, right? So this chain reaction, we call it a chain reaction because one step leads to another step and another step and so on. Now you would have met this already back in fifth form. Now we are going to go a little closer, a little deeper with this reaction. We are going to work out its mechanism. Now when I say mechanism, I mean what is going on at the molecular level, which bond breaks first, which bond forms first, and so on and so forth. A step-by-step account of what is taking place at the molecular level. Now, like I said, with each of these equations, they're just a summary of what is going on. So we're going to spend some time talking about this first reaction here, just to form monochloromethane. So we're not going to go so much into the others. Let's look at the mechanism of this particular reaction. All right, now the mechanism for the chlorination of methane involves the formation of what is called a radical. We can say free radical or just a radical. So what's a free radical? That is a species with an unpaired electron. A species with an unpaired electron. Unpaired electron. So as long as you have a single electron somewhere in there, you have a radical. Okay, so look at this, the chlorine atom. Chlorine atom has 7 electrons on its outside shell. So then we would pair them up like this, 2 here, 2 here, 2 here. We have 1 left on that side. So this is a radical. Chlorine free radical, it has an unpaired electron. Okay? Now, alkyl groups like methyl, for example, methyl, that can be a radical too, because what you really have is a pair of electrons being shared. So a shared pair, right? And then we have an unpaired electron right there, right? See the unpaired electron? So this is a radical. And when you think about it, any atom from alright, students. So like I was saying, the radicals, so any species, any atom from group 1, right? So all those group 1 elements would have an unpaired electron. They have 1 electron on their outside shell. Group 3, group 5, group 7, like the chlorine, right? All of these would atoms, since they have odd numbers of electrons, one of those electrons would be unpaired, and so they will be radicals. All right, so back to our mechanism now for the monochlorination of methane. Well, it involves the formation of a free radical. In fact, that is the very first step, and that is why we need UV light present, because the UV light is what helps to form this radical. So, step 1, what's happening in step 1? Splitting of the chlorine molecule into 2 chlorine free radicals. That's what is going on, right? So, we have our chlorine molecule. Now, I am using this sort of diagram. It's called a Lewis structure, right? To show those electrons. You know that each chlorine atom has 7 electrons on its outside shell, and then of course it would pair up with another chlorine to form the chlorine molecules, and they share this pair between them. So this pair right here is being shared between them, and all of these are lone pairs. Okay, now when the chlorine molecule splits, so like I said, step 1, splitting of chlorine molecule into 2 radicals. That's what goes on to step 1 of this mechanism. It's a homolytic splitting, or we say homolytic fission. Homo means the same, hetero would be different. So heterolytic splitting would be like this. The molecule splits into 2 pieces, and you have one that has 6 electrons and the other one that has 8. That would be heterolytic splitting, uneven splitting. But that is not what takes place in this mechanism. It's a homolytic splitting. So we end up with 2, it splits like that, right? So we end up with 2 chlorine atoms, each with their 7 electrons on their outside shell. It splits evenly. The bond, the electron pair that they're sharing between them, splits evenly. This chlorine atom gets back its electron, that chlorine atom gets back its electron. And so we have 2 chlorine radicals as a result. Now, how do I depict this sort of homolytic splitting in my mechanism? Well, here are 2 things you need to know. We use some curly arrows to show the movement of electrons in a mechanism. So the arrow curves over like this. Now, if it's the movement of 1 electron, then I draw a single barb on the arrow. So single barb arrow is for movement of one electron. Movement of one electron. The double barb arrow, these curly arrows, notice how curly they are, right? And this is showing movement of an electron pair. Movement of an electron pair. So I can have it like that, or I can even shade it. That means double barb arrow, movement of an electron pair. When you have it like that, single barb, it means movement of one electron. Now I'm going to use this one for this mechanism because I'm showing the movement of each electron. So here this bond splits evenly. I am not going to use this to show splitting, no. I am going to simply show that the electrons move away from each other. So this particular electron goes back onto that chlorine atom. And this particular electron goes back onto that chlorine atom. All right? So in that way, I am showing that this bond splits evenly. One electron goes onto that one, the other electron goes onto that one. And so I end up with two chlorine radicals. Two chlorine atoms, they have their unpaired electron. Now I need UV light for that because the UV light provides the energy needed to split the molecule homolytically. That is the purpose of the UV, to split that molecule. All right? Now what happens next? By the way, step 1 is called chain initiating step, because of course it's a chain reaction. Step 1 starts the process, so it's the chain initiating step. That's what we call step 1. Chain initiating step. All right. Now let's move on to see what happens in step 2 now.